Today we will be starting with what we or you must have heard of called as a double integration type of problems. Now when we say double integration, first of all let us recall the particular word integration. Integration you must have studied earlier, and some notation like integral y dx, which was quite familiar. Now can we be calling this as a double integral? Answer is obviously no, because you will be saying that there is only a single integral set. But what about variables? We have got two variables over here. One is x and other is y. Now this particular y is actually function of x. And so this integral is actually integral fx dx. So there are no two variables. This y has to be always expressed in terms of x. This is a typical function that we always refer to, because it is y can be expressed in terms of x or x can be expressed in terms of y, and it is going to be a single integration problem. Integration by definition, you must be knowing it as area under the curve. Suppose this is the curve y equal to fx, and suppose these are the two limits x equal to x1 and x equal to x2. This is x-axis, y-axis, origin. Then when you refer to integral fx dx from x equal to x1 to x equal to x2, it will be considered as area under the curve y equal to fx from x equal to x1 to x equal to x2. This concept is very well known. And then we have also learned that integration is opposite to differentiation. We will have to recall the definition of dy by dx in this case, which is written as limit as delta x tending to 0, delta y by delta x. That is infinitesimally small change in y corresponding to infinitesimally small, that is tending to 0, change in x. It is change in y with respect to change in x is the definition. And we also know the fact that integration is opposite to differentiation. Opposite to integration. This concept is very well required when we proceed to the double integration, because the entire concept will be based on this part where we say that x is infinitesimally small or y is infinitesimally small. Here it is obvious that we are finding the area under the curve. That is a direct definition of integration that you must have heard of. In double integration, we will be normally solving the problems where the area over which it is to be integrated is specified. It's going to be a definite integral and not the indefinite integral. Again, the two terms which you must be aware of. In case of indefinite integral, we don't have limits for integration, and so whenever we integrate, the constant of integration will come into picture. But in case of definite integral, when you integrate, the constant value will come into picture, but as you substitute the limits, that is the upper limit value minus lower limit value, that particular constant of integration will get cancelled, and we don't have to determine that. It's going to be a complete numerical value as the solution. So far as double integration, which we are going to study over here, is concerned, all the formulae of single integration are applied as they are. That means the integration formulae are not different for single integral and double integral. For double integration, we will be using the same formulae like the ones which you have studied earlier, something similar to integral of dx is x, integral of x raised to n dx is x raised to n plus 1 upon n plus 1, What I am writing right now are the indefinite integrals, and we should not forget the constant of integration which comes into picture in each case. We also have a formula like integral dx upon x is log x, and when we write log over here, it means that it is log to the base e. General notation could be ln x. Ln means, as you are using the calculators, even on calculator you have ln separately and log separately. So ln means it is log to the base e, natural base. Log to the natural base is ln. Otherwise log is term used for base 10. We can also apply the same formula for dx upon root x as interpreted as x raised to minus half dx. Using the same formula, it will be x raised to minus half plus 1 divided by minus half plus 1 plus constant of integration, resulting in x raised to half, that is root x, upon half plus c. Ultimately the answer is 2 root x plus c. This is something that we have already studied. We have also formulae for integration of sin x, which is going to be minus cos x, integral cos x, which is sin x, integral of tan x is log of sec x, integral of sec x is log of sec x plus tan x, integral of cot x is log of sin x, and integral of cosec x is log of cosec x minus cot x. All these formulae are known to you, and the same formulae will be applied when we go for double integration. Now we will have to have some consideration as what this double integration could be, and then we can proceed with the actual problem solving. As I have said earlier, that the double integration problems are to be specified as so and so function is to be integrated over the area. When we say we want to evaluate, say double integral p of x comma y, some function dx dy, because we want to integrate it over the area, one of this integral corresponds to x and one of this integral corresponds to y. If such a thing is given, then it is not a complete problem. We will have to also have a definition over area, say enclosed by, say for example y equal to fx and y equal to gx. We can have the same curve y equal to fx, and there can be a curve like y equal to gx, and we want to integrate p of x comma y over this area. This is what the problem statement could be. Of course, this area will vary. There could be some straight lines coming into picture, there could be some circular parts, parabola, hyperbola and whatnot. All those things will come into picture, but the area specification is necessary, otherwise you cannot evaluate the double integral. Physical interpretation of this is a bit difficult, because for that you will have to understand something called as a point function. Point function is one whose value depends on its position, that is x comma y. Point function is one whose value depends on its position, that is x comma y. Here p is a function of x and y, that means it is a point function. Consider, for example, suppose this is the area that is given to us, and it is said that the density at a point is function of x and y, that is the distance from y-axis, which is x coordinate, and distance from x-axis, which is y coordinate. So density at a point can be calculated provided you know the coordinates. And then if I ask you to find out the mass of this particular area, then the problem cannot be solved unless you find out density at each point, and probably you will be thinking of, instead of finding the density at each and every point, let us consider one small area, infinitesimally small area of say dimensions dx by dy, and on this area we can say that the density is constant. Suppose, that is of course the assumption. And then if the density is constant, then if I note this density by rho, then mass of this area can be considered as rho into dx into dy, where rho by itself is calculated from the position x comma y. I repeat the entire problem. We are required to find out the mass of this area such that the density at every point is a function of distance from x-axis and distance from y-axis. That means it is a point function. When we go on calculating the density at one point, you will find that even if you consider the nearest point, the density is almost constant. Because I am going to consider very small area dx dy, I can make an assumption and say that density throughout this area is constant, and then density into the area will give us the mass. It is actually density into volume, but being a plane area, there is no third dimension, no depth. We can simply say that mass of this particular plate is going to be the density into the area, that is dx dy. And to find the mass of this entire plate, we will have to consider all such small areas and add them. Now this will certainly remind you the concept that summation of discrete entities can be approximated to integration. Sometime, somewhere you must have heard of this, that summation, when goes on infinitesimally small level, then it can be interpreted as integration. Here precisely the same concept we are going to extend and say that find out mass at every point and go on adding the masses of these small areas, and you will be getting the integration, that is the mass of the entire plate. That's the beginning of double integration, because then we will have to plan as how are we going to cover up this entire area. Though I have shown some small area of dimensions dx by dy, I get rho into dx dy as mass of it, and you are going to write it as summation of all such. But when you say summation of all such, you will have to specify what is the range of x, what is the range of y. But when you simply specify range of x and y as say constant entities, then range of x being constant, say from x equal to x1 to x equal to x2, and range of y being constant, say y equal to y1 to y equal to y2, will always give you the area which is going to be the rectangular area. Whereas what we have in this particular case is the areas are bound by the curves. That means you are not going to write the limits as the constant ones. Here one of the variable can be expressed in terms of others, because I can go up to, say if I consider a line like this or some small area having the dimension as or the width as dx, then to cover up all the rectangles, small rectangles of size dy each on this, I will have to consider the values of y from this lowermost point to value of y at the uppermost point, and then consider all these dy values, dx, that is x coordinate at that position, is constant. Remember that y coordinate over here and y coordinate over here has got different values than when I consider the summation of the areas over here, because this y is different and this y is different. Ultimately we come to the conclusion saying that if I am to take the sum of all these areas, at every point the lowermost value of y will depend on x coordinate at that point, and the uppermost value of y will also depend on x coordinate at that point. So in order to add all these small areas, we will think of going horizontally by taking every time a strip of width dx. This is where the double integration will actually start, because now I can say that to evaluate the mass of this particular plate, let us take strip parallel to y-axis. I don't mind even if you consider strips parallel to x-axis. We will be coming to such problems in the subsequent cases. But here I am going to take the strip parallel to y-axis of width dx, and as we recall back and say that dx is infinitesimally small area, and on this particular strip I can consider the x coordinate to be constant. So on strip x is constant and y will vary from, say, lowermost point to uppermost. But the lowermost point and uppermost points for that particular x coordinate are functions of x, because you are looking for y coordinates, and I can say that in this case y varies from, because on that particular strip y varies from y on the lowermost curve, which is y equal to gx, to y equal to fx, that is the upper curve. So on this strip we are covering all the areas of height dy each, and then we will be saying that to cover the entire area, the leftmost strip is at this particular point. Suppose the point over here is say x1, y1, the point of intersection, and this point is say x2, y2. Then the leftmost strip will be at x equal to x1, whereas the rightmost strip is at x equal to x2. So to cover the entire area where I want to add all these infinitesimally small area values for this particular function p of x, y, I will have to say that take a strip parallel to y-axis of width dx on which x is constant and y will vary from lowermost point to uppermost point. As per the figure, it is y equal to gx, which is the lower curve, to y equal to fx, and such strips are taken from x equal to x1 to x equal to x2, of course referring to the same figure, and hence we will be covering the entire area. As we cover the entire area by taking the strips, we can rewrite this given problem saying that it is p of x, y dx dy. It's time to write the limits, because based on this area the two integrals will have limits. Remember that as we have taken strips parallel to y-axis, the inner limits will be with respect to y, that is, these are going to be values of y. So inner integral will have limits on the strip. So on strip, what are the limits? And on strip, one variable is constant and other is varying. So you will have to write the limits of y in this case, and these outer integral will have the limits of the positions of strip, and that's going to be the leftmost strip to the rightmost as in our case. So we can simply note down one formula saying that inner limits will correspond to that variable to which strips are parallel. One simple rule will make our task very simple, and then this integral will be written as double integral from y equal to gx to y equal to fx, p of x, y dx dy, and such strips are taken from x equal to x1 and x equal to x2. Also the fact remains that you will have to integrate with respect to the inner limits first, or we can again say a rule that if the strips are parallel to y-axis, we should integrate with respect to y first. If the strips are parallel to x-axis, integrate with respect to x first. Nothing really depends on this particular sequence over here, whether you write it as dx dy or dy dx. Some of the maths teachers, they say that dx dy likho ya dy dx likho. It's not the case, because these maths people themselves are aware of the fact as whether you consider it as 3 into 4 or whether you consider it as 4 into 3, the answer is going to be always 12. So dy dx and dx dy, it is not indicating the integration sequence as such. Of course, when you want to integrate with respect to y, probably you will take all the terms of y and take that dy along with it and integrate it. But it doesn't mean that if the problem contains dx dy, then we should be integrating with respect to x, or we should be integrating with respect to y if it is dy dx. So here we will be always integrating with respect to that variable to which we have taken the strip as parallel. Strip parallel to y-axis, we should be integrating with respect to y. The inner limits will be always of y, and we will be talking about y varying from the lowermost limit of that particular area to uppermost limit, and these limits are not going to be constants because they are going to be functions of x in this case. Whereas such strips are taken from leftmost point to the rightmost point, that is x equal to x1 to x equal to x2. This is going to be the constant limits, and final answer is going to be a numerical answer without containing any value like x and y. Now when I say that we should be integrating with respect to y first, at that time x should be treated as constant. So even if the term is xy, the integration will be x into y square by 2. X for the moment will be considered as constant, and then we will be integrating this particular function. Once we get the integration, then for y we will be substituting fx as upper limit minus gx as lower limit, and then everything will be in terms of x. Forget any other representation. It is a single definite integral problem. Solve it and you will get the numerical answer to that particular problem. That is what the beginning of double integration could be. All those who understand this particular concept of taking the strip, and the purpose is to cover the entire area, probably none of the problem will be very difficult. Now obviously you will ask me as why I have taken function or the strip parallel to y-axis. It was the reason that I have written the functions as y equal to gx and y equal to fx. That means y can be expressed in terms of x, and here also y can be expressed in terms of x. Suppose the functions are written other way around, x as function of y and x as function of y, it will be better if we take strips parallel to x-axis, and on strip x will vary from x on this curve to x on this curve. Of course that is a subsequent discussion, but initially as long as possible we will probably stick to, though not as a rule, but for us the things will be pretty simple, that we will be taking strips parallel to y-axis and starting with the solution. After our first lecture on the double integration, today we will go ahead with some part that we have discussed in the very first lecture, that is to change the order of integration. When we talk about the problems related to the change the order of integration, it straight away means that if we are integrating with respect to x first, then we are required to integrate with respect to y first. We have also said that when the strips are parallel to y-axis, then we will be integrating with respect to y first. When strips are parallel to x-axis, we will be integrating with respect to x first. So if the given problem says that the integration is done with respect to x, then we are required to change it and say that the integration should be done with respect to y. In other words, from the limits we are required to find the area, and if the strip is taken parallel to x-axis, now we should be taking the strip parallel to y-axis and rewrite the particular integral. The problem over here may not be to solve the integral and get the answer out of it, but it will be simply to rewrite the given problem in a different form. Let us consider the first problem. It is integral minus a to a, integral 0 to y square upon a, some function f of x comma y dx dy. And the problem says that change the order of integration. Change the order of integration. Some observation will be required and some statements are to be written once again. For example, here it is not specified as whether these are limits of x or y or these are limits of x or y. So first observation that will be required is to check the limits and see whether any variable is appearing into it. So we say that limits are in y. Now in y means this particular limit. Limits are in y. Therefore these are values of x. And if the inner limit represents something like x equal to 0 to x equal to y square upon a, that means the strips are taken parallel to x-axis. This is because as we are integrating with respect to x first. So the strips are taken parallel to y-axis and such strips are from y equal to minus a to y equal to plus a, because now again the outer integral cannot be in terms of x, or it is not the values of x which we are mentioning over there. So the given integral can now be written as integral x equal to 0 to x equal to y square upon a and y equal to minus a to y equal to plus a, some function f of x comma y dx dy. Thus we say that the area is bounded by x equal to 0, x equal to y square upon a, y equal to minus a and y equal to plus a. As we rewrite this particular curve, x equal to y square upon a is nothing but y square equal to ax, which is a parabola. We start with the region of integration. So now the problem is reduced to the previous case. From the limits we have found the curves, the boundary curves. From there we will be again finding the area. We have already written that initially he has taken strips parallel to x-axis. Now we are required to change the order and take strips parallel to y-axis. So when we say y square equal to ax, the parabola is going to be like this. This is y square equal to ax parabola. The other limits, as we start from here, x equal to 0, that is y-axis. This is x equal to 0 line. X equal to y square upon a, parabola we have drawn. Y equal to minus a is going to be a line like this, and y equal to plus a will be a line over here. So the four curves are, this is one parabola, this is line y-axis, this is y equal to minus a portion, and this is y equal to plus a line. In other words, we find over here that the region of integration must be this, but that could be just our conclusion. we will have to actually check as per the strips that he has taken. He has taken strip parallel to x-axis and the strip begins at x equal to 0. So this is the start point on y-axis and the strip goes up to the parabola here, and over here also the strip is starting on y-axis and going up to the parabola. Fine. And y varies from y equal to minus a to y equal to plus a. Yes, our conclusion was right. He has taken strips in this manner. This is the area that is under consideration. Once we draw the area, then we will have to change the order and say that we will be taking strips parallel to y-axis. When we take strips parallel to y-axis, here we will find that the nature of the strip is going to be rather different in each case. When we consider strip parallel to y-axis in the first quadrant, it will start on the parabola and will go up to line y equal to a. Whereas in the fourth quadrant region, the strip starts at y equal to minus a and goes up to parabola. Of course, point of intersection also is going to play important role, because now such strips will be taken from x equal to 0 to x at point A or point B, which is going to be some constant value. Once we decide on this particular factor, we can as usual say that this is area 1 and area 2, and the given integral can now be splitted over the two areas, area 1 and area 2. So the given integral will be double integral f of x comma y dx dy over area A1 plus double integral f of x comma y dx dy over area A2. We will say take strip parallel to y-axis in each case, that is taking strips parallel to y-axis. Now the discussion will vary. On strip in area 1, y varies from y on parabola to y equal to a. Obviously, the limits will be y equal to under root of ax to y equal to a. Whereas on area 2, y is going to, the strip is going to begin at y equal to minus a and will be going up to the parabola. So in the second case, y will vary from y on line y equal to minus a to parabola, and so the limits will be y equal to minus a to y equal to not root x minus root x. This is obvious because the equation of the curve was y square equal to ax, and when you try to find y from it, it will be y equal to plus or minus root ax, and it will be your responsibility to check whether you are considering plus root x, that is in the first quadrant, or minus root x, that is in the fourth quadrant. Once we write the limits on the strip on each area, area 1 and area 2, we will go for the next discussion, that is such strips are taken from x equal to 0, that is known, to x on point A, to x at point A, or it could be point P. So we are required to substitute this particular equation, that is y equal to a, in the equation of the parabola. So y equal to a in y square equal to ax, if you substitute, you will get a square equal to ax, that is x equal to a. So the equation of this particular line is going to be x equal to a. So we can say that therefore such strips are taken from from x equal to 0 to x equal to a in area 1, and same is the case with area 2, that is such strips are taken from x equal to 0 to x equal to a. This is what we are required to deduce, and then what remains is simply to rewrite these integrals with the limits. And so the expected answer in this case, that is the given integral, can now be written as, so the given integral can now be written as integral of f of x comma y dx dy over area A1 plus double integral f of x comma y dx dy over area A2. In area A1, y will vary from minus a to y equal to minus under root ax, and such strips are taken from x equal to 0 to x equal to a, f of x comma y dx dy, plus on area A2 the strip will begin at the parabola, that is y equal to root of ax to y equal to a, and such strips are taken from x equal to 0 to x equal to a. It is f of x comma y dx dy, and hence the change of order of integration will simply mean that we are required to change the sequence of integration, that is to change the order in which we are considering the integration by considering the strips parallel to x-axis or y-axis. In the given problem, the strips were taken parallel to x-axis, that is from x equal to 0 to x on parabola, and y varying from minus a to plus a. Now we are rewriting the same by taking strips parallel to y-axis, where we find that the area is broken up into two parts because there are two types of strips, and ultimately we end up with the solution by taking the strips parallel to y-axis, splitting the area A into A1 and A2, and this is the expected answer. As the function is not given to us, we cannot integrate it, and the answer should be left in the same form. Now the next problem is again of the same type. We are required to change the order of integration. It is integral 1 to 2, integral 1 minus root of 2x minus x square to 1 plus root of 2x minus x square, f of x comma y dx dy. Change the order of integration. Again in this case, the limits are given in terms of x, and from that we can conclude as how the user has taken the strips. As the limits are in terms of x, strips will be parallel to y-axis because these are values of y. So on strip we can say y varies from 1 minus under root 2x minus x square to 1 plus under root 2x minus x square, and such strips are taken from x equal to 1 to 2. So our standard thing, which we will be repeating only once, limits are in x. So the conclusion, these are values of y, these are values of y, therefore strips are parallel to y-axis. On strip, y varies from y equal to 1 minus under root 2x minus x square to y equal to plus 1 plus under root 2x minus x square, and such strips are taken from x equal to 1 to x equal to 2. Now the boundary curves can be deduced. It is y equal to 1 minus under root 2x minus x square. So it will be y minus 1 equal to minus under root 2x minus x square. Squaring both the sides, we will get it as y minus 1 bracket square equal to 2x minus x square. And so it will be y square minus 2y plus 1 equal to 2x minus x square, and it will be x square plus y square minus 2x minus 2y plus 1 equal to 0. When we think of the second curve, which is y equal to 1 plus under root 2x minus x square, it will be again y minus 1 equal to root of 2x minus x square, and will come down to the same curve. That means limits of y are taken on the same curve. What is this particular curve? This curve is a circle having center at 1, 1. We know that the general equation of circle is x square plus y square plus 2fx plus 2gy plus h is equal to 0, whose center is minus f comma minus g, and whose radius is under root of f square plus g square minus h. So in this case, the center will be, you can compare minus 2f plus 2f with minus 2, and you will get f equal to minus 1. So center is 1, 1, and the radius will be 1 square plus 1 square minus 1, that is root 1, it will be 1. So it will be a circle having 1, 1 as the center and radius as 1. So the figure can now be drawn as a circle which is going to touch both the axes. A circle whose center is 1, 1. So we have y-axis, x-axis, origin, center is 1, 1. This is point obviously 0, 1. This point is 1, 0. And if at all we are interested in locating this point, it is 2, 0, whereas this point is 2, 1. So from limits of y, we could draw the curve, and then he is writing limits of x as x equal to 1 and x equal to 2, and those two lines are respectively, this is x equal to 1 line and this is x equal to 2 line. How he has taken the strips? From 1 minus under root, that is curve to curve, the strips are taken parallel to y-axis. So his strip starts on the circle and ends on the circle, and such strips are taken from x equal to 1 to x equal to 2. Ultimately, this semicircle is the region of integration. If this semicircle is region of integration, and then we are required to change the order of integration, probably job is very simple and straightforward. We are required to take strips parallel to x-axis. So we can now write it as, taking strips parallel to x-axis on strip, x varies from x equal to 1, because it starts on the line x equal to 1 here every time and is going up to the circle, to x on circle. And such strips are from y equal to 0, the lowermost strip, and as radius is 1, this point is going to be 1, 2, or this line could be y equal to 2. So such strips are taken from y equal to 0 to y equal to 2. X on circle is to be calculated. We have the equation of the circle as we have written it just now. It is x square plus y square minus 2x minus 2y plus 1 equal to 0. From this, if we are required to calculate x, it will be x square minus 2x plus 1 is equal to 2y minus y square, that is x minus 1 bracket square equal to 2y minus y square, or x minus 1 equal to plus or minus under root 2y minus y square, and x is equal to 1 plus or minus under root 2y minus y square. So there are two values of x which are possible. One is less than 1 and other is greater than 1. Obviously we are talking about x which is greater than 1, and so the given integral can now be written as x equal to 1 to x equal to 1 plus under root 2y minus y square, and such strips are taken from y equal to 0 to 2. It is f of x comma y dx dy. This is the required solution. Let us now consider the next set of problems, and all these problems are again talking of the same question, that is to change the order of integration. Now we are not going to see the solution as a full, but there will be a procedure which we are going to discuss over here, and you will have to accordingly proceed. Observe that in first integral, limits are in terms of x. That means these are values of y. So the boundary curves can now directly be written as limits are in x, these are values of y, and so boundary curves for the first problem will be y equal to x square to y equal to 2 minus x. Both the curves can be well understood, and the outer limits are of x, that is x equal to minus 2 to x equal to plus 1. So the four curves are y equal to x square, x plus y equal to 2, x equal to minus 2, and x equal to plus 1. Out of these, the line x plus y equal to 2 is the line which passes through 2, 0 and 0, 2. So it is going to be a straight line like this, x-axis, y-axis. This is point 1, 1 which is onto it, because we require the line x equal to 1 also in this case, and we also require the line x equal to minus 2. Of course this point can be substituted in the equation of line. X is minus 2, so y will be 4, so it is minus 2 comma 4. So where these boundaries are intersecting, if we note these points, then parabola y equal to x square is well satisfied by these points, and the curve parabola will go like this. Oh, this particular curve, this particular problem we have just seen in the previous lecture. Once we draw the figure, it starts from y-axis, strips are parallel to y-axis starting from parabola to line, and then this was the region of integration. Such a problem we have solved in the previous case by considering both the areas, that is parabola to parabola will be one strip and parabola to line is the other type of strip. So the first problem can be very easily solved. As we proceed to the second problem, again observe that the problem is like this: integral 0 to 5, integral 2 minus x to 2 plus x, p of x comma y dx dy. Limits are in terms of x, so strips are taken parallel to y axis. On strip, y varies from y equal to 2 minus x to y equal to 2 plus x, and such strips are taken from x equal to 0 to x equal to 5. The boundary curves are now x plus y is equal to 2, first one, y minus x is equal to 2, the second curve, x equal to 0, third curve, and x equal to 5, fourth curve. If we try to plot these curves, x plus y equal to 2 is the line which we had discussed in the previous problem also, passing through the points 2, 0 and 0, 2. So this is point 2, 0 and this is point 0, 2. Fine. What about this line y minus x equal to 2? It passes through point, if I put x equal to 0, that is y-axis equation, then y will be 2, so it passes through 0, 2. And if I put y equal to 0, I get x equal to minus 2. X equal to minus 2 is this point. So the second line is going in this direction. So this is y minus x is equal to 2. This is x plus y equal to 2. And then he is talking about values of x from x equal to 0. He is talking about values of x from x equal to 0 to x equal to 5. From x equal to 0 to x equal to 5. This is line x equal to 5. If I substitute x equal to 5 in the equation x plus y equal to 2, then I will find that y comes out to be minus 3. So this is point 5 comma minus 3. And if I consider the equation of x equal to 5 with line x minus, or rather y minus x equal to 2, I will get the value as 5 comma 7. Y coordinate will be 7. However, his strips starting from the line y equal to 2 minus x, that is beginning on this strip, this particular line, and going up to y equal to 2 plus x. So the strips are in this manner, starting from x plus y equal to 2, that is y equal to 2 minus x, to y equal to 2 plus x, that is this line, and the region of integration in this case will be this triangle. Of course, when we try to take strips parallel to x-axis, the region will be divided into two parts, area 1 and area 2. In case of area 1, when you take the strip, it will be obviously starting from line x plus y equal to 2 and going up to x equal to 5. Whereas in area 2, when you take the strip, it will be starting on line y minus x equal to 2 and will be going up to x equal to 5. The respective limits of y for area 1 will be from minus 3 to y equal to 2, whereas in the second case it will be from y equal to 2 to y equal to 5. And the answer can now be written in the straightforward manner as, after changing the order of integration, the given integral can be written as, first of all, area 1. So it will be x coordinate from line x plus y equal to 2, that is x is equal to 2 minus y to x equal to 5, and such strips are taken from y equal to minus 3 to y equal to 2. It is p of x comma y dx dy. plus the second integral on area 2. It will be x coordinate taken from the equation y minus x is equal to 2. So it will be x is equal to y minus 2. So it will be x is equal to y minus 2 up to x is equal to 5, and such strips are taken from y equal to 2 to y equal to 7, p of x comma y dx dy, and we get the changed order equation. Let us proceed to the third problem. In the third problem, now the limits are in terms of y. So these are values of x. So the strips are parallel to x-axis. On strip x varies from under root a square minus y square to x equal to y plus a, and such strips are taken from y equal to 0 to y equal to a. X equal to under root a square minus y square can now be written as x square equal to a square minus y square, which is nothing but x square plus y square equal to a square, which is a circle with center as origin and radius as a. So such a circle can be drawn. Whose center is at origin, whose radius is a. The second curve, that is x is equal to y plus a, can now be found out, because when you substitute y equal to 0, that is to find intersection with x-axis, you will get x equal to a. So the second line passes through point a0, and if you substitute x equal to 0, you will get y as minus a, so it passes through 0 minus a, and so the straight line that he is talking of over here is passing through point 0 minus a and a0, which is the straight line x is equal to y plus a. The equation of the circle, as we have already noted, it is x square plus y square equal to a square. He has taken strips parallel to x-axis, and on strip the strip x coordinate varies from circle up to the line, and that too in the region y equal to 0 to y equal to a. Y equal to a is this line. This is line y equal to a, whereas this was line x equal to y plus a. His strip begins on the circle and goes up to the line, that limits are always from left to right. So he is beginning the strip over here and going up to the line. Ultimately he is talking about the region like this. Can be considered as one of the tough problems, because now we are getting some area which is not as obvious as it could be in any of the previous problems. Let us redraw that area. So we will be having a circle of radius a. Entire discussion is actually over. We will be drawing a circle of radius a and x-axis, y-axis. We also know that this point is a0. We know that the straight line that he is talking of is this way, that is passing through a0 and 0 minus a. This topmost point is 0 comma a, and the line y equal to a passes through it. This was our line x is equal to y plus a. This is origin, x-axis, y-axis, and he is taking strip which is starting from the circle and going up to the line. This was the region. Now as we take strips parallel to y-axis, we will be interested in basically this particular line, which is x equal to a, which is separating the two areas. This is area 1 and this is area 2. We would also be interested in this particular point whose coordinates, as you substitute y equal to a in the equation of line, it will be x equal to 2a. So the point is 2a comma a. We will be taking strips parallel to y-axis in area 1 as well as in area 2, and the two types of strips are different. In area 1 it is from circle to the line y equal to a, whereas in area 2 it will be from x equal to y plus a line to y equal to a. And so the answer can now be written as the given integral will be equal to y on the circle, that is under root a square minus x square, to y equal to a, and such strips are taken from x equal to 0 to x equal to a. Function is q of x comma y dx dy, plus double integral. It will be y coordinate from equation of line, which will be y equal to x minus a to y equal to a, and such strips are taken from x equal to a from this limit up to x equal to 2a. It is q of x comma y dx dy. One of the areas which are not very well expected for us. Based on change the order of integration, we could be having a problem as is shown over here, that is express the following integrals as single integral term and evaluate. That means these two integrals which have got the common function should be simply expressed as the double integral x square plus y square dx dy, and then it should be evaluated. But you can see that the limits are not the same one, so you cannot directly write it. So in other words, we are required to go for finding the areas and probably change the order of integration. Now limits are in terms of y, so I will talk about this as area 1 for integration and area 2 for integration. We will mark the areas one by one so that our task could be simpler. For first area, limits are in y, so these are values of x. So for first area he is talking about x equal to 0, which is y-axis, and x equal to y, which is a line making 45 degrees passing through origin. So this is x equal to y line. So he is taking a strip from y-axis up to this line in the region x equal to, or rather y equal to 0 to y equal to 1. This is line y equal to 1. And so we can say that the strip which is parallel to x-axis, starting from y-axis going up to the line from y equal to 0, that is x-axis, to y equal to 1. So the region of integration for the first integral is as shown in the figure. It's a triangle. The point of intersection over here is obviously 1, 1. Whereas in the second integral, it is again limits are in terms of y, which are values of x. So it starts from the same curve x equal to 0 and goes up to the line x equal to 2 minus y. The straight line x equal to 2 minus y is actually x plus y equal to 2, which passes through point 2, 0 and 0, 2. Obviously it passes through 1, 1 also. So a line which passes through 2, 0 and 0, 2, and he is taking the strips from y equal to 1 to y equal to 2. So this is line y equal to 2. His strip is parallel to x-axis from x equal to 0 to x on this particular line, which is x plus y equal to 2. And the region For second integral, area 2 is as shown in the figure. Once we get these two areas which are adjacent, and as the function for integration is just the same, that is x square plus y square dx dy, we can change the order of integration. That is, now we will plan to take strips parallel to y-axis and try to rewrite the integral. It will be take strips parallel to y-axis. On strip, y varies from y on this particular line, so that is y equal to x, to y from this equation of line, that is y equal to 2 minus x, and such strips are taken from the leftmost at x equal to 0 and the rightmost at x equal to 1. This is that x equal to 1 line. And the function to be integrated is x square plus y square dx dy. So the first part of the solution will be over, that is express it as a single integral, single term, and then evaluate. Now as the strips are parallel to y-axis, we are required to integrate with respect to y first. Integration of x square with respect to y is x square y, and that of y square will be y cube by 3, and it will be within limits x to 2 minus x dx. As we substitute the limits, it will be integral 0 to 1 x square into 2 minus x value at upper limit plus the second term value at upper limit 2 minus x bracket cube upon 3 minus values at lower limit, it will be x cube plus x cube by 3 dx. The solution can now proceed in the normal way and you can obtain the required answer. So it can be now written as integral 0 to 1. If I multiply by the terms, it will be 2x square minus x cube. Second term will stay as it is, 2 minus x bracket cube upon 3, and the lower limit term is actually 4x cube by 3 to be subtracted. So it is minus 4x cube by 3 dx. So for integration now we have integral 0 to 1. This is minus 4x cube by 3 and minus x cube will be minus 7x cube by 3 plus 2x square plus 2 minus x bracket cube upon 3 dx. Integration will be minus 7 by 3 x raised to 4 by 4 plus 2 into x cube by 3 plus 2 minus x bracket raised to 4, original 3 is already there, and minus 4. It is x raised to 4 upon 4 is the formula, and coefficient of x minus 1 we should multiply. As we substitute the values of upper limit, we will be getting it as minus 7 by 12 as the first term. I am substituting x equal to 1 plus 2 by 3 as second term, and the third term it will be 2 minus 1 means 1, so it is minus 1 by 12 as the third term. Minus at lower limit, when you substitute x equal to 0, first term is 0, second term is also 0, whereas third term will be 2 raised to 4 upon minus 12, that is minus 16 by 12. So this will come out to be minus 7 by 12 minus 1 by 12, so it will be minus 8 by 12 plus 2 by 3, and then this is minus minus plus, it will be 16 by 12. So this is ultimately minus 2 by 3 plus 2 by 3, this will cancel, answer will be 16 by 12, that is I suppose 4 by 3. How? Let us go through the entire problem. We are required to merge. So the problem is in front of us. We are given two different integrals. From there, we had drawn the two areas, area 1, area 2. The strips were parallel to x-axis, so there were two types of strips, two integrals. We had changed the order and we get a unique type of strip starting from x equal to y, from line x equal to y to x plus y equal to 2, and so from there we get the limits of integration. As y equal to x to y equal to 2 minus x, x equal to 0 to 1, and then we follow the integration procedure.